Welcome back. This is our second explanatory video. This one corresponds to paragraph 2 of the booklet of chapter 7. And we're going to continue from where we left off. In the previous lesson we learned what effect forces have on speed. Actually the change on speed. And today we're going to see how we can use a formula to predict speeds when a certain force is working. What we concluded previously was that forces change the speed of an object. If there is no speed, if there's no force working on the object, that means that the force will remain the same. And it doesn't matter if there's no force because nobody's pushing on an object, or if there is no force because there are two forces working on an object but they cancel each other out. The effect is the same, there's no force, so the speed remains the same. We're going to see a simulation and determine what factors are important when you want to predict the final speed of a box gliding on a frictionless plane. So we're going to use the same simulation again as in the previous video, the box and on a frictionless plane, and we're going to see what factors are important. Now I'm going to set up a timer so we can see how long we are pushing on the object. So, and we'll make sure we know the speed. Let's first figure out what the force itself means. So we're going to push for 5 seconds with 100 newtons, and then we're going to push for 5 seconds with 500 newtons. Okay, and go. 2, 3, 4, 5. Okay, so we've just passed the third mark. Now we'll reset, and this time we'll use 500 newtons. Okay, and here we go. And we reach the final mark. So, pretty obvious, when we push harder, the final speed will be higher. What of course is also important is how long you are pushing. So I'm first going to push for 2 seconds and then 4 seconds. So okay, and here we go. 1, 2. Okay, so we're about halfway. And now we're going to push for 4 seconds. 1, 2, 3, 4. And we reach the final mark. So the longer you push, the faster the box will go. Then the last one. The mass of this crate is 50 kilograms, so let's add an extra 100 and see what difference does that make. First, of course, without the 100 kilograms, I forgot that. So we're going to push for, let's do 3 seconds. Now. Okay, so we reached this tick. And now we're going to put the bin on top. So it's 3 times as heavy now. 1, 2, 3. And our speed is much lower. So the higher the force and the longer the time, the higher the speed that you will get. And the higher the mass, the lower the speed that you will get. This formula sums it up quite nicely. The force that I'm pushing with times the time that I'm pushing should equal the mass times delta V. And delta V means the change in speed, the final speed minus the starting speed. If I'm using a large force, that means this side of the equation will be a high number. If the mass doesn't change, that means delta V must also be a high number. Same if I push for a long time, then this will be a large number. That also means that delta V must be a large number. However, if I do not change force and time, and I keep making the mass larger and larger, then delta V must become smaller. This can easily be seen if I choose, for example, a force of 10 Newton and a time of 1 second. If the mass of the object I'm pushing is 1, that means the change in speed must be 10 meters per second. However, if the force and time are the same, but the mass is now 2 kilograms, then the change in speed must be 5, because 2 times 5 equals 10. So the larger the mass, the lesser the change in speed. If I start out with a speed that is 0, then the formula becomes a bit easier, because if this value is 0, then I'm multiplying with 0, and that also always gives a speed of 0. So I lose this part, and I get this formula. F times t equals m times v end. This is a bit easier. However, I do have to be careful. There are situations where the starting speed is not 0. Okay, so here's a little example. We want to calculate how long it will take to accelerate a 50 kilogram box from standstill to a speed of 40 meters per second with a force of 500 newtons. So I'm taking the equation, I'm going to fill in the numbers. We're pushing with 500 newtons, and we don't know how long we are doing that, because that's what we want to calculate. But we know the mass, that's 50 kilograms, and we know the speed, 40 meters per second. 50 times 40 equals 2000. Now, we need to bring the 500 to the other side, so we get the time it takes is 2000 divided by 500. If I type this in, I get a result of 4 seconds. So, you see, you can easily calculate any number as long as you know all the others. Here's another example. We are going to throw a pumpkin to the ground, and we want to know with what speed will it hit the ground. I have a simulation here that shows us the situation. Here it is. So we have a cannon here, and normally it would fire a pumpkin like this. However, if I'm making the initial speed, that's the speed with which it is launched, 0, then the pumpkin will simply drop to the ground. As you can see, it is dropped from 10 meters height. The mass is 5 kilograms. And here I can see the path that the pumpkin is taking. Simply dropping. Now this meter can tell me how long that took. It took 1.43 seconds for the pumpkin to reach the ground. Those are all the numbers that I need. So, let's do the calculation and see if we can calculate how quickly it felt, with what speed it hit the ground. The force working on the pumpkin is the force of gravity, which equals 10 times the mass. Now the mass was 5 kilograms, so the force working on it would be 50 newtons. We can fill that in. The time was 1.43 seconds, and the mass we just seen was 5 kilograms. We can bring the 5 to the other side of the equation, so that would give us 50 times 1.43 divided by 5. This I'm typing into my calculator. It results in a final speed of 14.3, rounded off 14 meters per second. Okay, this is all good, but is it true? Because the simulation has no speedometer, so I need a way to calculate the speed in a different way to check if I did it correctly. Well, we can use old theory for that. We already learned how to calculate average velocity from covered distance and time. The covered distance was the height, 10 meters. And the time was 1.43, which gives us an average velocity of 0.7, not 0. Excuse me, that was incorrect, of 7 meters per second. Okay, now, may seem as if we're failing horribly. However, I have not calculated the final velocity. The pumpkin starts out with a speed of 0 and it smashes into the ground with a much higher speed, which we do not yet know. What we calculated was the average velocity. So we're going to use this formula. Average velocity is 7 meters per second. Starting velocity is 0. We are going to solve for v end. And we need to divide by 2. If I'm going to bring the 2 to the other side, I'm going to get 2 times 7 equals 14 meters per second, which should equal v end. And that is exactly what our other formula told us. So the two theories match. To conclude, you can calculate final velocity using the formula F times t, which means the force with which I'm pushing times the time that I'm pushing, and that should equal the mass of the object I'm pushing times the change in velocity. Is my starting speed, or v begin or v start, is that 0? Then the formula becomes easier. It's F times t equals m times v end. And that also concludes this video. Thank you for watching and see you all in class.